Hello once again, phenomenal ladies and gentlemen. It's Matufaro here and welcome back to my space. This is the latest video in the virtual series where we're looking at a problem set of questions, and at this moment we're going to look at some questions on limits. Without wasting much time, let's get right into it. The first question here, we are told to evaluate the limit of 10 to the power of t minus 2 to the power of t minus 5 to the power of t plus 1 over t tan t as t approaches 0. And as usual, the first thing to try is to see whether a direct substitution will work. That is, we need to plug in t equals to 0. So direct substitution will yield 10 to the power of 0 minus 2 to the power of 0 minus 5 to the power of 0 plus 1 over 0 times tan 0. And this will give us 1 minus 1 minus 1 plus 1 over 0 times 0. And that is 0 over 0. Oh, that is an abomination. That is one of the 7 deadly sins, one of the indeterminates. So this is an invitation for us to use L'Hopital's rule. We could actually first and foremost check if there is anything we can do without using L'Hopital's rule at all. But looking at this, I don't think there is anything we can do, as an elementary function that will totally evade the use of L'Hopital's rule. Let's go directly with L'Hopital's rule. Maybe after that, I will come back to try to factorize things and see where we can go. So we can use L'Hopital's rule because we have an indeterminate 0 over 0. So let's say I'm using L'Hopital's rule. We know that this limit as t approaches 0 of 10 to the power of t minus 2 to the power of t minus 5 to the power of t plus 1 over t tan t is equals to the limit as t goes to 0 of the derivative of the numerator. That is what the L'Hopital's rule says. It says when direct substitution will yield 0 over 0 or infinity over infinity, then the limit is equal to the limit of the derivative of the numerator and over the derivative of the denominator, which is what we want to see here. So recall that the derivative, so if y is equal to a to the power of x, its derivative, y prime, is a to the power of x natural log of a. Also, if y equals to tan t, y prime is equals to sec squared t. So let's just have that in our toolbox. We'll come back to it. So here, the derivative of the numerator, so we are still going to drag along our lim t approaches 0. So using what we've seen here, that will be 10 to the power of t times natural log of 10 minus 2 to the power of t times natural log of 10 minus 5 to the power of t times natural log of 10 plus 0, because 1 is a constant. And in the denominator, this is a product of two functions, so we have to use the product rule. So that is u times the v dx. So you remember that if y equals to u times v, then y prime is uv prime plus vu prime. So which is what I'm using here, where this is our u and this is our v. So v prime, according to what I've written by the side here, is sec squared t, then plus v, which is tan t, times the derivative of t, which is 1. So again, we attempt direct substitution. What are we going to get? If we do direct substitution, this is going to give us 10 to the power of t is 1, same as 2 to the power of t and 5 to the power of t. So, I've made a mistake there. This should be natural log of 2, and this should be natural log of 5. All right, so if 10 to the power of t and 2 to the power of t and 5 to the power of t are both 1 when t equals to 0, then we are going to be left with natural log of 10 minus natural log of 2 minus natural log of 5 over, then if t is 0, 0 times anything is 0, and tan 0 is 0. What does that numerator lead to? So using the laws of logarithm, log a minus log b is equals to log a over b. That tells us that log 10 minus log 2 is log 10 over 2, which is log 5. So if this is log 5, ln 5, so log 5 minus log 5 is going to be equals to 0. So this is 0 over 0, another indeterminate, which means we can use L'Hopital's rule again. Using L'Hopital's rule again, this will be the derivative, the limit as t approaches 0 of the derivative of the numerator 10 to the power of t natural log of 10 minus 2 to the power of t natural log of 2 minus 5 to the power of t natural log of 5 all over the derivative of t times sec squared t plus tan t. Okay, so what is the derivative here? So this is the limit as t approaches 0. Again, the derivative of 10 to the power of t is 10 to the power of t times natural log of 10. So if we multiply that by natural log of 10, that gives us 10 to the power of t times natural log of 10 squared. Then the same thing here, 2 to the power of t times natural log of 2 squared minus 5 to the power of t times natural log of 5 squared. Okay, so natural log of 10 is a constant, so we do not have to use the product rule here. So we know that the derivative of a constant times a function is just the constant times the derivative of the function. So in this case, ln 10 is the constant, and if we find the derivative of 10 to the power of t, we get another 10 to the power of t ln 10. So the ln 10 multiplies each other and gives us ln 10 squared. The same thing with the ln 2 and the ln 5. In the denominator, we have a product here, so we are going to use the product rule again. But we need to remember that the derivative of sec t is sec t tan t. So the product rule here, u and v, u times dv dx, so that is t times, so to differentiate sec squared t, we can also use the chain rule. So that is going to give us 2 sec squared t tan t. So that is simply a result of the chain rule. When you know that sec squared t can be written as sec t squared, so if we use the chain rule, so this will give us 2 times sec t raised to power 1 times the derivative of sec t, which is how I got what is inside the bracket here. Then that is u dv dx plus v du dx. V is sec squared t, and the u dx is just t, it's just 1. So we have found the derivative of this to be this. Then the next part is the derivative of this. So we're going to have plus sec squared t, since that is the derivative of tan t. So we can now try the direct substitution one more time. Let's see if we are going to need to continue doing L'Hopital's rule or it ends here. So if we plug in t equals to 0, we get 10 raised to the power 0, which is 1. So we end up with natural log of 10 squared minus natural log of 2 squared minus natural log of 5 squared divided by, so t, in the one in blue, the first part, t times anything, when t is equals to 0, all of those will go away, plus sec squared 0. Sec squared 0 means sec 0 squared plus sec 0 squared. So that's 2 of them. Okay, so let me just write it out. Plus sec 0 squared. But what is sec 0? Sec 0 is 1 over cos 0. Since cos 0 is 1, this is 1 over 1, which is 1. So, and also we remember that natural log of 10 is natural log of 2 times 5, which is natural log of 2 plus natural log of 5. That means the numerator here is going to be natural log of 2 plus natural log of 5 squared minus natural log of 2 squared minus natural log of 5 squared. Everything over 1 plus 1. We are getting there. So when you look at that numerator, you see that if we let ln 2 to be a and ln 5 to be b, this is a plus b squared minus a squared minus b squared. But what is a plus b squared? That is a squared plus b squared plus 2ab. So if this is this, and we subtract a squared and b squared, so this cancels out, we are left with 2ab. So that means our numerator here is going to be 2 natural log of 2 times natural log of 5 divided by 2. So the 2 cancels out, and we are left with natural log of 2, natural log of 5 as the answer to the limit question. So the alternative way would be to try to factorize the numerator. So alternatively, if we say limit of t as t goes to 0 of 10 to the power of t minus 2 to the power of t minus 5 to the power of t plus 1 over t times tan t. I think that's correct. Good. So we can actually factorize the numerator. We have already seen that the direct substitution will give us 0 over 0. So a factorization of the numerator in the sense that 10 to the power of t is the same thing as 2 times 5 to the power of t, and that is 2 to the power of t times 5 to the power of t. So if I have 2 to the power of t times 5 to the power of t minus 2 to the power of t minus 5 to the power of t plus 1. So this is like ab minus a minus b plus 1. And if we group this, if we pair this up, a is common here. So we have a b minus 1 and negative 1 b minus 1. So it can be factorized as a minus 1 b minus 1. So the same thing can happen here. So this is limit as t goes to 0 of 2 to the power of t minus 1 and 5 to the power of t minus 1 over t tan t. How does that help us? So we know that we can actually split these things up. So because this is equal to the limit as t to the power of 0 over, so then we have 2 to the power of t minus 1 over t times 5 to the power of t minus 1 over t times t over tan t. I have done some manipulation there to introduce a new t. Because why have I done that? Because I can split this thing into something that is really interesting. So this is 2 to the power of t minus 1 over t times the limit, using the limit laws, 5 to the power of t minus 1 over t times the limit as t approaches 0 of t over tan t. Now, if we like, or we can now use the L'Hopital's rule here, because 2 to the power of t is 0, when t is equal to 0 is 1 minus 1, and that will give us 0 over 0. So that's grounds for using L'Hopital's rule. The same thing with the expression in the middle, and the expression in the last expression itself is one of the main common limits. So just as we know that limit as x goes to 0 of sine x over x is equal to 1, when we have t over tan t or t over sine t, it is also equal to 1. So in this case, if we use L'Hopital's rule for the three of them even, so using L'Hopital's rule, so this is the same thing as limit as t goes to 0 of the derivative of the numerator. Derivative of 2 to the power of t is 2 to the power of t times natural log of t over 1. The same thing with the second term. That will be 5 to the power of t times, why am I writing in t? In 2, in 5 over 1. And the last one, in t, limit of t goes to 0 of 1 over sec squared t. So I have used L'Hopital's rule on 3 of them. I think this is an easier application of L'Hopital's rule than the first method. So when we apply t equals to 0 now, we get 2 raised to the power 0, which is 1, times natural log of 2. So this is 2 raised to the power 0 times natural log of 2 times 5 raised to the power 0 times natural log of 5 times 1 over sec 0 squared. And we've seen before that sec 0 is equal to 1. So it means our answer again is natural log of 2 times natural log of 5. All right. Then the next question, which is about exponential functions. So we want to do exponential x squared minus cos x. So b, the limit as x approaches 0 of exponential x squared minus cos x over, did I get that right? Yes, over x squared. Good. Of course, direct substitution will immediately tell us that it is an indeterminate form. When x is equals to 0, we have e raised to the power 0 minus cos 0, which is 1 over 0 square, and that will give us 0 over 0. So it's an indeterminate form. We cannot factorize here, we cannot rationalize, we cannot use conjugate, so we are only left with the option of using the L'Hopital's rule. Because we have 0 over 0, we are good. So using the L'Hopital's rule, we know that the limit as x approaches 0 of e to the power of x squared minus cos x over x squared is equals to the limit as x goes to 0 of the derivative of e to the power of x squared minus cos x over the derivative of x squared. And this is equal to the limit as x goes to 0. So if we take the derivative of e to the x squared using the chain rule, we're going to get 2x times e to the power of x squared. Generally, the derivative of e to the power of f of x, where f of x is any function of x, is always equal to the derivative of f times e to the power of f of x. And that is what I've used here. The derivative of f of x here is x squared, and its derivative is 2x. So that gives us that. And the derivative of cosine of x is negative sine x. So this is going to be plus sine x over 2x. Now, if we plug in x equals to 0, that gives us 0 plus 0 over 2 times 0, 0 over 0. We use L'Hopital's rule again. So using L'Hopital's rule again, this is equals to the limit as x approaches 0 of the derivative of 2x e to the power of x squared plus sine x over the derivative of 2x. So here we have to use the product rule for 2x times e to the power of x squared. So again, 2x e to the power of x squared. This is our u, this is our v. You remember that is uv prime plus vu prime. So we're going to have uv prime, that is u, that is 2x times the derivative of e to the power of x squared. We've done it, 2x times e to the power of x squared. That is my uv prime plus vu prime. So let me shift this a little bit so that things do not collide. Plus vu prime, that is going to be the derivative of u, which is 2, times v. So that is 2 e to the power of x squared. Then the derivative of sine x is cosine of x. Then in the denominator, the derivative of 2x is 2. Now we can plug in x equal to 0. So plugging in x equals to 0, the first guy will go away because x times 2 and x is equals to 0, everything will be equals to 0. And the second guy, we're going to have 2 times e raised to power 0 plus cosine of 0 over 2. That is 2 times 1, 2 plus 1 over 2. And the final answer is 3 over 2. And without wasting much time, with the last question, x plus sine x, x plus cos x. So as the x approaches infinity, x plus cos x. So in this case, we are going to direct substitution will give us infinity over infinity. So we have to be creative with our manipulations. So the first thing we can try to do is to factor out, the highest power of x like we usually do. But in this case, let's just say factor out x from both numerator and the denominator. In both the numerator and the denominator. So what do we have? So this is the limit as x approaches infinity of x over x. In the numerator, we have 1 plus sine x over x. And in the denominator, we have 1 plus cosine of x over x. So the x's can now cancel out, which means we are left with the limit as x goes to infinity of 1 plus sine x over x over 1 plus cos x over x. But hold on, what is the limit as x goes to infinity of sine x over x? You remember when it is limit as x goes to 0 of sine x over x, we said this is equal to 1. But what happens when we go to infinity? So sine x is something that is usually between -1 and 1. But so the sine x is fixed in between -1 and 1. But x, which is the denominator, is something that is, as x goes to infinity, the denominator is blowing up. And anytime you have a case like that, when the denominator is blowing up, it means that the whole fraction is going to go to 0. Okay, so the same thing happens with cosine of x over x. So when you have a fraction and you're taking the limits, if the denominator runs faster to infinity than the numerator, in this case the numerator is not even going to infinity, it is stuck, it is bounded between -1 and 1. So it means the limit here is equal to 0. And that tells us that the final answer here is 1 plus 0 over 1 plus 0, which is 1 over 1, which is equal to 1. And this video is long enough. I think this has been the longest in the series already. So it's good. It's a good place to stop so that we can go to the next one in the next video. But if you have any question or anything you want to point out in what we have done here in the 3 limit questions, do not hesitate to write down in the comment section and we can discuss about it. And until the next video, take care and continue to enjoy mathematics. Bye.